Welcome back to Chem 4300. In this video, we're going to continue the topic of chemical kinetics, and now we're going to look at predicting reaction orders. You may remember from your organic chemistry class working through reaction mechanisms, and that there were often many elementary steps that came together to form an overall reaction. We're going to build on that idea in studying kinetics, and we're going to classify those elementary steps in that mechanism as unimolecular, bimolecular, termolecular, depending on whether they involved one species reacting, say a molecule just sort of shaking apart, some kind of intermediate and forming a product, or two species coming together to form a product, or three species coming together to form a product. Each of those steps, those elementary steps that take place, will be unimolecular, bimolecular, termolecular, and so on. And when it's unimolecular, then the rate of that step will be given by a rate expression that is just a rate constant times the concentration of the one species that's on the reactants of that step. If it's a bimolecular elementary step, then it would be two species involved, and the rate would be some rate constant times the concentration of those two species. Now, we want to be careful and distinguish the word order from molecularity. When we're talking about an overall reaction and looking at its rate law, we'll use the word order to talk about the exponents that appear on all of the concentrations in our rate law. But when we're talking about an elementary step, we'll avoid the word order, and we're going to use the word molecularity instead. So this one has a molecularity of 1. Here A has a molecularity of 1, B has a molecularity of 1. If it was A and A coming together, then it would be A having a molecularity of 2, and so on. So just a subtle distinction there, but order and molecularity seem to be related, but they're different because molecularity is related to the underlying steps in the reaction mechanism. So if we have a situation where the overall reaction is limited by the overall reaction rate is limited by one of those elementary steps. So say you may have 4 steps, but one of those steps of the 4 is the slowest of all, then that's going to be the rate limiting step. And say that rate limiting step is unimolecular, then the overall reaction rate might look like it's first order. If the rate limiting step is bimolecular, then there's a good chance that your rate for the overall reaction is going to look like it's second order, or so on if it's termolecular. So let's take a look at some examples of some of these elementary steps. So if you can see for a unimolecular reaction, that's going to be some kind of decomposition reaction. So imagine this sort of unstable molecule N2O4 will react and decompose into 2 NO2 molecules, or this highly strained ring will decompose and turn into this chain molecule here. As an example of a bimolecular reaction, imagine deuterium colliding with a hydrogen molecule, knocking off the hydrogen and forming a DH diatomic molecule. Or an NO2 reacting with the carbon monoxide to form nitrogen oxide and CO2. These are all bimolecular because in this step, you can imagine physically this one approaching this species and forming this reaction. In a termolecular case, then you might have to imagine then a deuterium coming in, a hydrogen coming in, hitting a hydrogen molecule somewhere down here. That would be a termolecular reaction elementary step, and again, that would be sort of third order for that particular step. But we're going to use the word molecularity, so instead of order. Generally speaking, we don't have molecularities higher than 3, and particularly in the gas phase, it's hard to even get these kind of reactions in the gas phase. So most of the cases we'll be looking at will be either unimolecular, bimolecular, and occasionally termolecular. Now, let's look at some examples of elementary steps coming together to form overall reaction rates. So one sort of common example is a equilibrium reaction where A can go to B, but B can also go back to A. So in a sense, we have 2 steps going on. A going to B, B going to A, and there's a rate constant for each one of those steps So K1 is for A going to B, K minus 1 is for B going to A. And the ratio of those rate constants actually make what's called the equilibrium constant for this reaction. Now, if I was going to write out the rate expression, I would write down here that the rate of change of A, which is being turned into B, is going to be K1 times A minus K minus 1 times B. When I want to solve this differential equation, then what I'm going to do is look at this situation as a case where I'm going to be deviating away from equilibrium. So let's define a variable x that is the deviation of A or B away from their equilibrium values. So with this definition of x, I can rearrange it to get a concentration of A as equal to the equilibrium concentration plus that deviation, and similarly here for B, where now there's a negative sign here. So using this definition in here, I can take that side of the equation and expand it out, and I get dx dt, and then I get this term here, which is a constant because this is the equilibrium value, which is not going to change. And then on the other side, over here, I'll plug in this expression, and then I'll get this term here. So expanding that out, then I'll get this term plus this term, and you'll recognize that this term here is just the forward rate and the backward rate, and at equilibrium, we expect those rates to be equal to each other, so this and this will cancel each other, and that term will go to 0. So that leaves us only with this term, so now we have our differential equation that we're solving for this particular problem. That has a very trivial solution here, which is just this exponential decay away from back to the equilibrium value, which is defined here as x naught. So if we go back and resubstitute in, this is what we would get for the concentration of A as a function of time as it is deviated away or perturbed away from its equilibrium value. It will relax back with an exponential recovery that has a constant here of 1 over K1 plus K minus 1. So if I describe this as e to the minus t over tau, then the relaxation time, or the time constant for that recovering back to equilibrium, is given by the inverse of the sum of the rates. Now, that was for one particular case where the rate, we looked at the recovery like this, but it really depends upon the molecularity of the reaction. So in this case, we looked at this simple case where it just A goes back and forth to B. If you took this case here where A and B react to form C, and then C goes back to A and B, you could also describe that in a very similar treatment, and you would derive that the time constant for that, it would give you the same kind of a result, but the time constant would be given by this expression here. So this I'll leave for you as a homework assignment. Now we come to a really sort of common problem that I want to go through in detail here, and then we're going to look at some approximations. Now, this is a reaction mechanism where A goes to some intermediate, and the intermediate goes to a product, but the intermediate also has the possibility of going back to A. So if we were going to write down the rate based on the concentration of the three species, the rate of change of A is going to be minus K1 times A here, plus K minus 1 times I going back. And for I, we have K1 times A forming I, and then we have I going back to A, so that becomes minus K minus 1 times I. And then we have I going to P, so that becomes minus K2 times I. And then finally for P, we have P is just being formed, so it's just going to be K2 times I. And now we set up our differential equations. We have three coupled differential equations that we have to solve for three concentrations. So this one is actually not very easy to do. And I'm just going to give you the solution, and then later we'll look at some approximations. So if you have the initial condition where everything is A and there's zero I and P present, then this is what the solution looks like. You have to do some kind of integration by partial fractions. Don't worry about it. I'm just giving you the solution here, just to show you that it's possible to solve this. And what I'm going to do is plot this as a function of time so you can see what the concentrations look like, because these expressions are probably not so intuitive. So if I just take this solution that we get by solving these couple differential equations and I plot it, it looks something like this. So here's the concentration of A, and you're starting out initially all with A, and as time goes forward, the A decreases exponentially. The P will increase with this exponential behavior, and then the intermediate down here will initially rise, and then it will stay at this very low level and decrease very, very, very slowly throughout this whole process. So this is sort of the exact solution that we got by solving those differential equations. But one thing you see here is that that intermediate concentration stays pretty low during the whole time that this reaction is taking place, and it can sort of be relatively constant during the time when these two guys, A and P, are varying the most. So this brings us to something called the steady state approximation. If the intermediate is so reactive that it stays at a low concentration, like that example I just showed you, then you can make what's called the steady state approximation. And it requires that K minus 1 plus K2 is much greater than K1. And if you make that assumption, then what happens is that this expression that we derived for di dt, so back here, if you go back to this expression, what we're going to say is that this concentration is varying slowly in the region of interest here, where it's varying very slowly, that we're going to say that it's approximately equal to 0. And what does that do for us? Well, we can take that equation and solve it and say that the steady state of concentration of I is approximately equal to this expression. And then armed with this expression, we can go back to these expressions for A and P, and we can substitute that steady state approximation in, and that gives us easier solutions. So taking the expression for A, substituting in this expression here for I, we get this equation here, which simplifies to this form. And then for P, we have this expression on the first couple slides back, and that goes into this form here. Now, I'm going to look at two additional simplifications. So one is if the first step is slow, so if K minus 1 is going to be much smaller than K2, then what happens over here is that K minus 1 can be ignored, and then we have only K2 in the denominator. That's going to cancel out, and our rate for production of P is just K1 times A. All right. The other possibility is that if the second step is slow, K2 is much smaller than K minus 1, then if K2 is smaller than minus 1, then that term goes away, and we're left with this ratio times K2, and that's given right here. That ratio you recognize as the equilibrium constant that I mentioned earlier, and then we have for the rate, that is that the rate of change of P is the equilibrium constant times K2 times A. So this is what we call the pre-equilibrium approximation. So this is a really common approximation that we'll be using as we look at some of the different examples here in the rest of this section. So that's it for this video. In the next section, we're going to use that to look at something called the Lindemann mechanism.